He's going to be our penultimate presenter for the day. So we have Fat Bo, and then we have one more. So if you're still here, you're still watching with us, please stick around for these final two, and then you're absolutely welcome to head over to the poster presentations, which will be ongoing for the next hour. So go ahead and take it away.
Okay. Can you see my screen?
Yep, we can see you and hear you as well.
Okay, thank you.
Oops.
I'm Fakfo. I'm a PhD student at the Department of Mathematics, West State University. Today, I would like to talk about a generalized Newton method for subradiant system. This talk is by on the joint work with Professor Boris Modokovic, who is my advisor, and Dr. Kanfam. Okay. Before moving on to our result, I would like to give you the outline of my talk. The first one, I want to talk about the motivation, why we have to study and establish our method. And after that, I will recall classical Newton method, which is the main idea to develop our methods and results. And after that, I will give you the computations for lots of problem, which play a crucial role in machine learning and statistics, and conclusion and future research. Okay. The first one, I want to talk about the motivation. We would like to establish a generalized Newton method for solving the optimization problem. The function f here is the quadratic functions. As you can see, this is the definition of quadratic function, and the function g here is the lower semi-continuous function, maybe not smooth. And this class is labeled as problem of quadratic composite optimization. Okay, and this function is not need to be convex function. Okay. And the motivation here, why do we have to solve this kind of optimization problem? And the reason is the problem of the above type frequently appear in practical models of machine learning and statistics. I will give you some other important classes of problem arising in practical modeling to illustrate uh, our considered optimization problems. The first one is regular least square problems. So you can see in the screen that's either least square problem, and this problem is the quadratic composite optimization problem, and it appear in machine learning statistics and used for image processing. And the second one is support vector machine problems. And you can see this is the model for support vector machine problem. And the code function here is, as you can see, is the sum of the quadratic function and the non-smooth function. And the final one is the constraint quadratic optimization when the function tree is the indicator function. In this case, we have the quadratic composite problems. Okay. And the second one, I will recall the classical Newton method for solving the gradient system. Here is the classical Newton method. Is used for solving the gradient gradient system tree, and the classical Newton method is generated by this sequence. And the result in the classical result is this algorithm is locally well defined and superlinear converges to a solution x bar of the gradient system tree if we have the assumption that the Hessian matrix is not singular. Okay, the idea here, we want to develop the classical Newton method for solving non-smooth optimization problem. uh, uh, so the question here is, how do we develop the Newton method in the case the function phi is not smooth? Okay, that's either the question. That's either research question. And the idea here is to replace the Hessian matrix by a generalized Hessian, because in the case the function phi is C2 smooth, it is not smooth. We will not have the Hessian matrix, so we will replace it by the generalized Hessian. And the idea here, we will use the generalized Hessian is the second order subdifferential, which was introduced by Modovic in 1992. In his paper, he used the second order subdifferential to analyze the sensitivity in non-smooth optimization. Okay. Why we have to use this? Well, we have to use second order subdifferential because the second order subdifferential have a lot of advantages. The first advantages here is uh, second order subdifferential have a comprehensive calculus rule, sum rules, different rules, quotient rule, chain rules, and so on. And the second order subdifferential can deal with a non-convex optimization problem, not just convex optimization problem. And second order subdifferential have the explicit calculation of the second order subdifferential in the number of settings important for application. Okay, that's all the things about the advantages, and there are lots of other advantages, but I will not mention here because of the time. Um, so I will give you the first algorithm of our result. The first one is the algorithm one for solving the gradient system when the function phi is C11 smooth. In this case, we just relate the Hassan matrix by the second order subdifferential, as you can see in the equation 5. And the result here, it is similar to the classical case. Our algorithm is also locally modified and superlinear converges to a solution if if we have the assumption like this. And the second algorithm, we will solving the quartic optimization problem. As you can see in the screen, that is the algorithm for solving quartic optimization problems. And the result here we got here is similar to the classical case. The algorithm 2 also locally well-defined and superlinear converges to X bar if we have three assumptions here. And finally, we apply our algorithm to solve completely the lasso problem, which play a crucial role in machine learning and statistics and used for image processing. And result we got here is the algorithm 2 for solving lasso problem is efficient. The efficient here means that our algorithm will attain the superlinear convergence rate when we have the assumption that the metric a star A is positive definite. Okay, and we also give the code for this, and you can use MATLAB to run the algorithm for solving this problem, and it's published on the website here. And the conclusion, in this research, we developed the following. The first one, we established a generalized Newton method for solving C11 smooth optimization problems, and so that our method is efficient. That means we get the superlinear convergence rate. And we also established the Newton method for solving quartic composite optimization. And final one, we provided the explicit code and competition for lasso problems. In the future result, we want to apply our algorithm to solve completely the practical problem, including support vector machine problems, constraint quartic optimization problems, clustering, so on. And not only quartic optimization, we want to develop the others non-smooth optimization problems. Okay, that's all the thing we want to do in the future. Thank you for your attention.
Thank you so much, Fat. That was really great. I know last year you had a similar, a separate presentation that was that also addressed some of these problems. So this was really good. I'm looking over in the chat. I don't see any questions. I think the chat at least is slowing down, but again, you're still getting the typical congrats and the high fives. So really well done, Fat. And we'll move on to our final speaker of the day. At least here at the platform presentation level, this is Sachithra. You've been waiting for a while.